Imagine hiring a sous chef who has, only ever been taught how to blindly chop carrots.
Right, just endless, mindless chopping.
Exactly. They have never turned on an oven. They've never tasted a dish. And, they have never even read a recipe.
Not a single one.
But after standing in the corner and just quietly watching the kitchen operate for a week, this chef suddenly steps up to the counter and bakes a flawless Michelin star souffle.
Which makes absolutely no logical sense.
None at all. You didn't teach them how to do that. They just absorbed the underlying logic of cooking simply by observing everything at once.
Yeah, they figured out the rules just by watching the data flow by.
Okay, let's unpack this, because that impossible scenario is actually the closest way to understand how the defining technology of our era was actually built.
It really is the perfect analogy for what we're looking at today.
Welcome to this custom-tailored deep dive. Today is Thursday, May 28, 2026. And tomorrow, Tech Reader magazine is officially dropping a highly anticipated, long-form essay by Aaron Rose.
Yeah, it's titled, How ChatGPT Was Built, Part 1. The idea that started everything. And we were lucky enough to get early access to the piece.
And it is a phenomenal piece of forensic tech journalism. We all interact with these systems daily now, but Rose really deconstructs the precise, agonizing timeline of how this technology was wrestled into existence.
He really does. It's fascinating to see the actual history laid out like that.
Right. And our mission for you today, as you listen, is to use this essay to completely shatter a very persistent Silicon Valley myth.
Oh, the myth of the lone genius.
Exactly. We all know the trope, right? The lone genius working in a garage, staring at a whiteboard until a light bulb suddenly goes on. The triumphant eureka moment.
Yeah, that's almost never how real engineering works.
No, it's not. And this deep dive is going to reveal the exact opposite. We are looking at a story of sustained uncertainty, a massive 5-year gamble against the consensus of the entire industry.
And crucially, the specific 15-page Google paper from 2017 that made modern AI possible.
Yes. Because there is this massive, jarring contrast between how magical ChatGPT felt when you first used it and the grueling, highly experimental reality of its construction.
To fully grasp the magnitude of what OpenAI eventually achieved, we really have to travel back to the technological landscape right before 2017.
Okay, set the scene for us. What was going on?
Well, the entire artificial intelligence industry had essentially hit a brick wall, and they were heavily reliant on an approach called supervised learning.
Supervised learning. That sounds incredibly clinical, but in practice, supervised learning was basically a massive digital sweatshop, wasn't it?
That is actually a very accurate way to describe the labor involved. It was tedious.
How so?
Well, if you wanted a computer system to simply recognize a stop sign, you couldn't just describe a stop sign to it.
Yeah, you can't just say it's a red octagon.
Exactly. You had to physically gather hundreds of thousands of images, and then you needed human beings to sit at computers and explicitly draw boxes around the stop signs. Yeah, this is a stop sign. This is a yield sign. And the machine would eventually learn to recognize the mathematical patterns in those human-provided labels.
But that creates a highly specialized, incredibly narrow tool, right? Like an idiot savant that can spot a stop sign with superhuman accuracy, but has absolutely zero understanding of what a road is, what a car is, or what stopping actually means.
Precisely. And that narrowness was the real bottleneck. The industry knew that supervised learning would never lead to general adaptable intelligence.
Oh, so what was the alternative?
The dream, what researchers actively referred to as the holy grail of machine learning, was unsupervised learning.
Okay, so dropping the humans from the loop.
Exactly. The goal was to create a generalized model that could learn from raw, unlabeled text. No human categorizing, no hand-holding.
So if supervised learning is like forcing a kid to memorize a million highly specific flashcards,
Right.
Unsupervised learning is like dropping someone in the center of the world's largest library and saying, figure out the rules of human thought, grammar, and logic just by reading everything.
That's it. You feed it raw data and tell it to do one single thing. Guess the next word.
Just guess the next word.
Yeah. By constantly guessing the next word and then seeing if it was right or wrong based on the actual text, the system forces itself to develop a broader understanding of context.
Okay, but wait. If the library approach, this unsupervised learning, is clearly the path to general intelligence, I just don't get why the smartest engineers on the planet wasted a decade building digital flashcards.
It seems backward.
Yeah. It feels like they were intentionally taking the slow route.
Well, they didn't really have a choice. They were trapped by their own hardware and software architecture.
Oh, interesting. How so?
Before 2017, the dominant method for processing language was through structures called recurrent neural networks, or RNNs. And there was a slightly more advanced variant called LSTMs.
Okay, RNNs.
Yeah.
What was the problem with them?
The fatal flaw of an RNN is that it processes data exactly the way human beings read a book sequentially. Left to right, one single word at a time.
Which intuitively feels like the right way to build a language machine, right? Since human language is a sequential stream of information.
It feels intuitive, but computationally it creates massive fragility.
Like what?
Think about it. If the machine is reading one word at a time, it has to carry the memory of the first word all the way to the end of a long paragraph.
Oh, I see.
By the time an RNN reached the final sentence of a page, the mathematical memory of how the page started had essentially degraded. The context evaporated.
So if the old RNN method was like trying to read a dense novel through a tiny moving peephole.
That's a great way to picture it.
Yeah, looking at just one word at a time and desperately trying to remember the plot. But the larger issue was how that peephole method interacted with the physical computers, right?
Yes, the physical hardware constraint was the absolute killer here. The engines in the modern AI revolution are graphics processing units, or GPUs.
Right, the chips used for gaming.
Exactly. Originally designed for video games to render millions of pixels on a screen simultaneously, GPUs are massive parallel computing chips. They want to do thousands of calculations at the exact same time.
But an RNN, by definition, is a one-thing-at-a-time sequential machine.
Bingo. It couldn't utilize the parallel power of the GPU. Training these models was excruciatingly slow, and whenever researchers tried to make the models bigger,
The whole system just choked.
it choked completely, so the entire field was stuck in the mud, totally unable to utilize the very hardware that was supposed to propel them forward.
And Google actually solved this hardware problem almost by accident, right? Publishing the answer in an open access paper during the summer of 2017.
Yeah, it was a huge turning point. 8 researchers at Google Brain in Mountain View quietly uploaded a document to Arsfov.
That's the bare-bones server where scientists post their pre-publication research, right?
Exactly. And it was remarkably unassuming. Just 15 pages of text, a few architecture diagrams, some equations, and a small block of open-source TensorFlow code.
But it carried this incredibly confident, undeniably provocative title, "Attention is all you need."
It was a bold claim. And inside OpenAI, which was still a very young, relatively small San Francisco organization at the time, their chief scientist, Ilya Sutskever, read that document.
And Sutskever was already highly respected for his earlier work on neural networks.
Very much so. And his reported reaction to this 15-page provocation was immediate. He basically looked at it and said, "Oh my God, this is the thing."
He recognized instantly that this wasn't an incremental tweak to the RNN. It was a complete demolition of the sequential reading problem.
That's right. The paper introduced an entirely new architecture called the transformer.
The transformer, which basically takes that tiny moving peephole, throws it in the trash, and looks at the entire page of text all at once.
What's fascinating here is the specific mechanical innovation they introduced called self-attention.
Self-attention. Okay, break that down for us.
Because the transformer drops the left-to-right processing entirely, it ingests the whole sequence of text simultaneously. It then calculates mathematical relationships between every single word and every other word in that sequence.
Generating what they call attention scores.
Exactly.
Let's ground that in reality for a second. How do attention scores actually parse language? Give me an example.
Sure. Think about the word bank. If a transformer looks at a paragraph and sees the word bank in the same block of text as the word river or water, it calculates attention scores that heavily link those concepts.
Ah, so the model mathematically understands the context is geography.
Right. But if the word bank appears near the word money or vault, the attention scores shift dramatically. The context is finance.
That's brilliant.
And because it analyzes the entire text simultaneously, it can make that critical distinction regardless of how many paragraphs separate those contextual clues.
And because the transformer analyzes everything simultaneously, it perfectly aligns with the hardware.
Yes, the sequential bottleneck is dead.
You can suddenly distribute the workload across thousands of parallel processing GPUs. The speed limits just vanished overnight.
They did. But you know, the broader research community looked at the transformer paper and mostly saw a highly efficient translation tool.
But Sutskever and the team at OpenAI looked at it and saw a completely different horizon.
They did. They realized that if you have an engine that can process raw text at unprecedented speeds, You could finally push unsupervised learning to its absolute limits.
But having a faster engine doesn't mean you automatically know where to drive. The next phase required a foundational wager that went aggressively against the grain of expert consensus.
It really did. The conventional wisdom across the machine learning landscape was that scaling up models would quickly hit a wall of diminishing returns.
Meaning they thought getting bigger wouldn't make it much smarter.
Right. The consensus was that if you keep making a model bigger, it gets marginally better for a while, but eventually you just waste millions of dollars on electricity for no real gain in intelligence.
But Sutskever vehemently argued the exact opposite. His contrarian bet was shockingly blunt. Just make it bigger, and the capabilities will naturally emerge.
His intuition, built over years of working in the trenches of deep learning, was that scale itself possessed a kind of magic. So OpenAI adapted the transformer architecture to do just one thing: predict the next word.
They gathered astronomical amounts of raw, unlabeled internet text, and they began to build. They rebuilt the entire transformer architecture from scratch using PyTorch.
Which is a highly flexible coding framework used to construct complex neural networks.
And this kicks off a timeline of aggressive, almost relentless scaling. In 2018, they released GPT-1.
Right, and GPT-1 had 117 million parameters.
To hear that word constantly now, but what is a parameter in this context?
Think of parameters as the digital synapses of the AI. They are the microscopic, adjustable mathematical knobs the model turns to make a decision.
Okay, so the more parameters a model has, the more nuanced and complex its brain is.
Exactly. At 117 million parameters, GPT-1 was tiny by today's standards, but it successfully proved the concept. Unsupervised pre-training on raw text worked.
So they doubled down. By 2019, they released GPT-2, and the scale jumps dramatically, from 117 million parameters to 1.5 billion.
A huge leap.
It is. It's also at this stage that they refine how the model digests language. Instead of predicting full words, the model is trained to predict tokens, which are essentially fragments or chunks of words.
And this was the moment the output shifted from mechanical text completion to something genuinely eerie.
Here's where it gets really interesting. GPT-2 wasn't just predicting the next token in a sterile way. It was writing coherent, sustained prose.
It was shocking.
You could prompt it with the first sentence of a fake news article, and it would convincingly finish the entire piece, inventing quotes and maintaining the narrative tone. It could write short stories with actual arcs.
In fact, OpenAI was so alarmed by the leap in quality that they initially refused to release the full 1.5 billion parameter model to the public,
citing severe concerns about the mass generation of deceptive information and deepfakes.
Right, and that decision triggered an absolute firestorm of debate within the research community.
Oh, I remember.
Many critics accused OpenAI of executing a brilliant public relations stunt to hype their own technology,
while others completely agreed that the safety risks of mass-produced misinformation were catastrophic. And looking back from where we are now, it's clear the industry is still fiercely debating whether that initial fear was justified or overblown.
Very much so.
But impartially speaking, regardless of the motivations behind the withholding, the very fact that researchers were arguing over the societal danger of a text predictor tells you that the capability of the technology had crossed a major threshold.
Oh, absolutely.
The writing ability wasn't programmed. It was an emergent property of the scale.
The pattern was undeniably established. The transformer architecture wanted to scale, and scaling relentlessly produced massive surprises.
Which brings us to the true earthquake in this timeline. The year 2020. OpenAI launches GPT-3.
The big one.
We go from 1.5 billion parameters to an absolutely staggering 175 billion parameters, more than 100 times larger than its predecessor.
And at 175 billion parameters, the capabilities did not just scale linearly, they became qualitatively alien.
Alien in what way?
GPT-3 suddenly started performing arithmetic. It was writing highly functional computer code in languages like Python. It was translating fluently between French and English and summarizing deeply complex legal documents.
I have to push back on this because it defies common sense.
I know it does.
They feed this massive supercomputer an ocean of raw internet text. They give it one single instruction, guess the next token. And suddenly, it knows how to write software and do math.
It sounds impossible.
Yeah. Guessing fragments of words does not teach you calculus.
It doesn't make sense until you reframe what guessing actually requires when operating at a 175 billion parameter scale.
Okay, help me reframe it.
Think about what it takes to accurately predict the next word in a high-level physics textbook. The model can't just rely on statistical parroting of letters. Eventually, To make the most mathematically accurate guess possible, the neural network is forced to build an internal representation of the laws of physics.
Wow.
It isn't copying code or math, it is literally reverse engineering the underlying logic of reality just to win the game of predicting the next token.
The logic, the coding, the math, they're unavoidable byproducts of deeply understanding human language.
Yeah.
It is the chef figuring out the souffle just by watching the kitchen.
Exactly, but having a machine capable of doing that and having a machine that a human being can actually use are two drastically different things.
That's a great point.
GPT-3 was an utterly disorienting system.
Because it wasn't a product at all. It was an API and application programming interface. Basically, a raw, exposed digital pipeline that developers could plug into.
Right, it had no conversational wrapper, no friendly interface, and absolutely no safety guardrails.
If you asked it, how do I boil an egg? It might respond with, how do I boil a potato? Simply because it thought it was continuing a list of rhetorical questions.
It was an alien intelligence locked in a server room. It was a genius, but a terrible, uncooperative tool.
So the researchers realized they had won the wager on scale, but now they had to figure out how to teach this alien entity human manners.
They had to close the massive gap between a raw text predictor and a genuinely helpful assistant.
And according to Aaron Rose's essay, achieving that required two excruciating behavioral innovations between 2021 and 2022. First, they developed instruction tuning.
Right. Instead of letting the model blindly complete sentences, they began feeding it a highly curated data set of tasks phrased as explicit commands.
Like summarize this article or translate this paragraph.
Exactly. They were fundamentally teaching the model the concept of human intent. It learned that when it receives a command, it is supposed to execute the request, not just add more words to the prompt.
That makes logical sense, but the second fix, which was required to make the model safe and pleasant to use, sounds like a logistical nightmare.
Oh, it was.
RLHF, reinforcement learning from human feedback.
This was the crucial punishing step. OpenAI hired armies of human annotators to interact with the model, review its outputs, and meticulously rank them.
Asking questions like, was this specific answer helpful? Was it polite?
Was it factually safe, or did it provide instructions on how to build a weapon?
Think about how hard it is to teach a new human hire, the subtle vibe or the unwritten cultural rules of your workplace. What kind of joke is appropriate in a meeting versus what is completely out of line.
Right, it takes months for a human to learn that.
Now imagine trying to codify that subtle human intuition mathematically into the weights of a multi-billion-dollar supercomputer. That is essentially what RLHF is doing.
And it was an agonizingly slow, high-stakes process. Those thousands of human rankings were used to train a secondary system called a reward model.
And the reward model then acted as an automated grader, continually scoring the main AI's behavior.
But every single flaw or bias in that human-trained reward model propagated directly into the final system.
Oh, so if the human graders naturally preferred longer answers, the AI would quickly figure out how to game the system.
Exactly. It would write incredibly long, sycophantic, overly polite paragraphs that didn't actually answer the question.
It constantly exploited the loopholes in the reward model.
Yes. The engineering feedback loops took weeks. It burned millions of dollars in computing power and required a level of patience that almost broke the teams working on it. But they had to align the model's behavior with human expectations.
And the culmination of all that painful tuning was a model called InstructGPT, released quietly in early 2022.
It was dramatically more useful, it actually followed instructions, and it had functional safety guardrails.
It was the direct technical ancestor to ChatGPT.
Which perfectly sets the stage for the launch.
November 30, 2022. OpenAI launches ChatGPT. It is essentially a fine-tuned version of that GPT 3.5 architecture, wrapped in a deceptively simple, incredibly familiar chat box user interface.
A text box that responded in a completely natural conversational register. It completely hid the staggering complexity, the GPUs, the billions of parameters, and the RLHF tuning beneath a blank white screen.
And the adoption rate remains hard to comprehend. It hit 1 million users in 5 days.
Which is just unheard of.
It absolutely obliterated the historical growth records of consumer platforms like Facebook, Instagram, and TikTok. And the reason it exploded is vital to understand. Suddenly, you had a tool that could hold fluid conversations, edit your professional emails, explain deeply complex scientific concepts, and write functional software, all in plain English.
Yeah, you didn't need a computer science degree or an API key to operate the most advanced technology ever created. You just had to know how to type a question. If we connect this to the bigger picture, you'll see Aaron Rose's core thesis in this tech reader essay becomes undeniable. The true story of ChatGPT isn't a singular breakthrough. It wasn't a bunch of coders having a eureka moment in 2022.
It is the story of sustained uncertainty. They didn't code a chatbot. They built a massive engine, and the chatbot emerged from it.
When Ilya Sutskever and his team read that 15-page Google paper in 2017, they had no idea that GPT-3 would eventually learn to write Python.
Right.
They just possessed an immense conviction that unsupervised learning was the correct path, and they had the relentless drive to build the infrastructure and test it at a scale no one else was willing to attempt.
From an unassuming paper uploaded to a server in 2017 to the fastest-growing consumer technology in human history, the real innovation wasn't just the transformer architecture itself. It was the willingness to bet everything on the power of scale, when the rest of the smartest people in the industry firmly believed it was a dead end.
Scale itself was the engine for discovery.
And that's the ultimate takeaway here. Whether you're prepping for a critical board meeting, trying to manage a team through a transition, or simply trying to understand the artificial intelligence that is actively reshaping your specific industry, the lesson is that true innovation rarely looks like a sudden stroke of genius.
It really doesn't.
It looks like a long, expensive, unglamorous 5-year grind toward a conviction you hold that others simply don't see yet. And by the way, Aaron Rose is dropping part 2 of this series soon, which will dive into the actual physical engineering pipelines, the massive data centers, the cooling systems, and the distributed computing networks that made this impossible scale a physical reality.
Which raises an important question for all of us to consider as these models continue their aggressive expansion.
Let's hear it.
If GPT-3 developed the ability to write code and perform logic purely by accident, just by absorbing enough data to predict the next token, what completely hidden emergent capabilities might a model 100 times larger naturally develop while we aren't looking? Are we fundamentally prepared for tools that develop profound skills we don't even know how to test for or measure yet?
So what does this all mean? It means the future belongs to those who are willing to bet on the unknown. Thanks for joining us on this deep dive.